Okay, so prepare yourself for action. This is question 11, the last question in 23.2. It goes beyond the exclamation mark. It's a horrific question. I have never seen a question as hard as this, or as involved, or as complicated as this ever. And this is very, very unlikely you get this in a paper. It's just beyond crazy, but does test an awful lot of what you need to know in this topic. Right, let's tackle it. In fact, I need to Google what a grain hopper was. I didn't know whether it was a solid lump of material. It wasn't obvious to me what it was. So, having done that, I was able then to do the maths of it. It says a grain hopper, and there it is, just the tub really, is in the form of a cylinder. There it is on top, with a frustum of a cone. Now, a frustum of a cone means you take an ordinary cone. Let's just draw it to the side here. Take an ordinary cone like that. This one's upside down, and then you cut it across like that, and you get like a baby cone left over like so, and you get this part left on top, which is what you see there. You get like a bit of a cone with its nose chopped off. So that's the bottom bit, and that's the top bit, and that's called the frustum. So if I underline that in blue, then that's the part I'm talking about there. Right. So here we go, a bit of a cone with the nose chopped off. Its measurements are shown faithfully. Now, each one of these is a mission in its own right. It really is. First question: what volume of grain will the hopper hold? Right, so therefore I can store grain in here. So if I can store grain in here, it looks like the bottom isn't like chopped off and left sealed. It's like I don't know, it's just got like a bottom to it like that, and that's a solid piece of metal there. Otherwise, if you put the grain in, it just falls straight through, wouldn't it? Which is stupid. So I've got, if you like, a flower pot with a cylindrical part on top. It's called a grain hopper. So that's the background to this awkward piece of mathematics. What volume can I hold? Well, two parts really. I've got a cylinder on top because it says so. Let's just do that really easily. So the volume of the cylinder, is pi times radius squared times the height, and that's going to be 3.14 times, well, the radius, the diameter is 1 meter across, therefore the radius is going to be half a meter, which is 50 centimeters. I'm going to stick to centimeters because all the other measurements are in centimeters. So pi times radius squared, which is 50 squared, times the height of the cylindrical part of this grain hopper, times 80, and that gives us a final answer of 628,000 centimeter cubed worth of volume. Okay, that's that done. Don't worry about big numbers. We can always trim it down to litres later, or meters cubed, or something like that. Not a problem. Now, I've got to work out the volume of this horrid shape here, known as the frustum of a cone. In other words, cone without the nose. Now, there is no direct formula, unless you want to construct one yourself, of working out the volume of this. So what I need to do is to treat it like two separate cylinders, as if this was happening. So if you imagine this was continuing down here, say, and that was continuing there, we have to imagine we've got two separate cones, and then we work out the two volumes of the two cones, which is easy, and then subtract the volume of the little one from the volume of the whole thing, and that will give me the volume of this frustum alone. That's not, but that causes even more trouble. Now, what we've got here, to work out the volume of a cylinder, of a cone, we need this formula here, don't we? We need, just write it in black here, we need to somehow employ volume of a cone is 1/3 pi times radius squared times the height. Tremendous. Well, I don't know the height from here to here to work out the big cone. All I know is the height from here to here, I believe, because if it's 150 from top to the bottom of the frustum, and the height of the cylindrical part is 80, I can merely subtract to get the height of the frustum. But this formula only caters for the formula for the volume of a cone, so I need to work some magic here. So check this out and watch the magic. Now, going from here straight to the bottom, and from here to the side, I've got a small one here as well. I'm creating, if you like, some what they call similar triangles. So I've got a big red triangle like that relates to this little triangle like that. As you can see, they expand and are drawn from a common point, the point there being the bottom of this imaginary cone here that I've chopped up earlier. So I need to do some mathematics with that, and let's use yellow so it stands out. Right, what is the radius from there to there? Well, the radius from there to there is 50, so it's going to be 50. Oh, that's terrible, it doesn't stand out. So it's going to be 50 from there to there as well. So we have a radius of 50 there, and again the bottom of the frustrum, or if you like the base of the baby cone, has a diameter of 50, therefore the radius is going to be 25. Is that alright? From there to there is 25, because right across it's 50. That's what we're told. Now I know this part of the height is 150 take away 80. In other words, that part is 70 alone. Alright? Now I've got to set up a little equation here. So I've got 50 relates to this entire the 50 relates to this 25 in the same way that 70 relates to the entire length from there to that tip there. Whereas you can see the enlargement is a scale factor 2 going from 25 to 50, or we can say the enlargement is scale factor half going from 50 to 25. Therefore I can see that the length from this point here to the tip is going to be twice as big as the length from this point here to this radius right there. So I know that the height is going to be 140. So let me try and put that in skillfully using a little diagram. So from here to here, again I'm really labouring this point, from here to here we have 140 centimetres, alright? Which makes obviously the bottom height of the bottom part of this cone also 70 centimetres. Sorry, I can't get rid of that 50, just leave it there for now. So I've got 50 radius, wide part of the cone, 25 radius, small part of the frustrum or radius of the bottom cone. I've got a height of 140 from that point to the tip, and a height of 70 from that point to the tip. So I've got myself, if you like, some similar triangles. I'm just going to draw it separately down the side, so just to get rid of every bit that seems difficult. So I've got that essentially, and I've got that across there, and I'm going to put the numbers on right now. So that's basically a 50, that's basically a 25, that's 70, and that's a mystery height h, also known as 70. Alright, now let's just do that. In fact, should I prove to you this is 70? I mean, should I? Maybe I should. Let's just do it up here then, shall we? So if we set up a little equation, we can see that the height, if I get rid of this 70, let me just prove it to you. So if I call this h or something like that, I could work out the mystery height there. Now look, we know that 25, if I work up here, again this is just one step, if I know that 25 divided by his little brother 50 is directly related to the small height h divided by his brother, which is called 70 plus h, I can rearrange a little equation like so, and then find out the actual height. Okay, so 25 over 50 is just like comparing the little height of the slower triangle divided by the true big height of the bigger triangle, which is part of the bigger cone, obviously. So rearranging this, taking this over and cross multiplying in the usual way. So you come over to here and multiply, you go over there. So I've got 25 lots of 70 plus height equals 50 lots of the height. Multiplying out, I go 1750 plus 25 lots of height equals 50 lots of height. Again, take this over and subtract it. I've got therefore 25 lots of my height is 1750. So the height, this little h part here, is 1750 divided by 25, and then that will in fact give me exactly 70 centimeters. Grab your calculator and do it, because I did. Right, so I've proved that h is in fact 70. Okay, as well. Now, I've got all I need to start rocking and rolling now. So I can work out the volume of the large cone. Remember where we're coming from? Volume of large cone, volume of baby cone, then take them away, and then I've got the volume of the frustrum, which is what I'm going to do. So let's just do volume of large cone then, and work in yellow down here. That's going to be, again we're using the formula here, V equals 1/3 times pi, which is 3.14 times the radius squared, and there it is, 50 squared, multiplied by the height of the big cone, which we've calculated as 70 plus 70, which is 140. Alright, now that will give us, because I punched it into my calculator, a big number, 366,333.3 recurring centimeters cubed. So 366,333.3 recurring centimeters cubed. That's the large cone. Now the baby one, again, V is going to be 1/3 times pi times the radius squared, which is 25 squared, multiplied by the height of the baby cone, which we calculated as 70 before, times 70. And that's going to give us, here we go, 45791.6 recurring centimeter cubed. In other words, 45,791.6 recurring centimeter cubed. I could have gone 0.7, but I can't bother to change it now. Now, what have we got therefore? If we subtract these two, we can find the volume of the frustum. So therefore, volume of what they called it, frustum. It's going to be a big one. Take away the little one. And this one I didn't calculate, or did I? Let me just check that. I'll do it now, because I did it in one big step, so I don't want that to happen. So 366,333.33333, and then we're going to take away 45791.66666, and that leaves me with 320,000. I've read that as a decimal point. 541.6 recurring centimeter cubes. Now that's that bit. Now don't forget, that's the volume of just this part here I've just calculated, and we also have the volume of the main part, which is the cylinder there, and there it is. So I must add it on. So therefore total volume is going to be the great big cylindrical part, so 628,000, add on the extra little bit there, 320,541.6 recurring, and that's going to give us a number in the 900,000, which it does. I make it 948 spot comma 541 point. Is that what I make it? 94. Yeah, I just did it in my head. 948.541.6 recurring centimeters cubed. Now that's it. That's the final answer. It's a little bit ugly. Do you recognise and do you recall and do you understand and accept that in fact that's equivalent to 948,541 point, let's call it 0.7 just by rounding, milliliters. It's the same thing. So a centimetre cubed is a milliliter, and if I divide that by 1,000, I'm going to get it into litres. So here I go. Get it into litres. So 948,451.7. So divided by 1,000, go back 1, 2, 3 spaces. I've essentially got 948.5 litres. Now, I don't know if the answer is meant to be in litres or meters cubed. If I want to put it into meters cubed, I'll divide by 1,000 again. And but I'll leave it like that. It's 948.5 litres, or 948.5. Well, no, litres is a really good unit actually. So leave it like that. That's my answer for part A only. And I think I better stop the video. It's getting really long. I will do part B on the other side, and I'll flick back to this page just to get some of the numbers that we used to, which we will need for part B anyway. So I'm going to stop that, and I'll get back to you quite soon.